Moving forward into chapter 7, I mentioned at the beginning of the semester that the class is sort of broadly broken into spectroscopy and separations. And so we're moving on with our spectroscopy course. And so that we did molecular spectroscopy with UV-Vis, and now we're moving on to atomic spectroscopy. That might seem a bit backwards. Why not start with atoms and build up to molecules? It turns out molecules are much easier to work with than atoms. And so the UV-Vis is probably a technique that most students are familiar with before they take this course, and so it's a more logical starting point. So that's one point where I do agree with the textbook. So as we move into atomic spectroscopy, we're going to take a look at some a little bit more refined instrumentation. The lab that we do will probably involve some AA this week. And so we're going to just have an opportunity to go through and talk a little bit about how atomic absorption is different from molecular absorption. Okay. Field raised his hand.
What is lab going to look like for Russ and I?
Yeah, so for the three of you that are remote, you are welcome to Zoom in during lab. But my plan is to just provide you with the data from someone who's there so that you can run the analysis. And we will do the sort of walkthrough of the instrument and sort of point out all the pieces and parts. And so if you're on Zoom for that, or FaceTiming with a fellow student, it doesn't really matter to me the platform we use, but as long as you're around for that virtually, I think that'd be good, so you can actually see some of the pieces of the instrument as we take it apart a little bit, and then hope nothing breaks. 2 years ago, I took apart the AA and broke a piece of it, so we couldn't use it. We hope that doesn't happen this year. All right, so yeah, AA. So I mean, hopefully by getting the data and the handout, you're able to follow through the process of calculating the amount of copper and nickel. We are figuring out the ratio of nickel and copper in a US nickel. So it's a fun lab because it always starts with dissolving a nickel. And people say, isn't that against the law? Well, no, it's not. You can't deface money and then try to use it as real money, but I don't plan on taking a volumetric flask full of dissolved nickel anywhere and saying this is 5 cents. Okay, so moving right along. All right, we are in chapter 7. Hopefully you found these all right this morning. Oops. For my Gen Chem lab on Thursday, I rearranged all my windows, and now I gotta get things back in order. All right. So AA. First things first, we gotta compare it to what we know, right? We're gonna make some connections here to UV-Vis. We're going to try to, find some similarities and then broad out into some differences. And so in UV-Vis, maybe some columns are useful. In UV-Vis, we're looking at molecules, right? Whereas in atomic absorption, obviously we're looking at atoms. Right? And because of that, we can't get any molecular information, right? We start with molecules, but what we're doing is we're essentially doing our best to break those molecules down into individual atoms. And so we lose all molecular information. And so it's AAS is used when we're interested in individual element concentrations, or if we're concerned about it's used a lot in heavy metal analysis, that kind of thing. It's not used so much for elemental analysis. Maybe you remember a Gen Chem problem, probably a hard problem, where it talked about a percent composition due to elemental analysis, and you got a molecule that produced 0.68 grams of CO2 and 1.4 grams of H2O and maybe that's it. And then you had to figure out from that the empirical formula of the compound. AAS is not good at that. There's a table in our textbook. I didn't put it in these slides, but there's a table in our textbook of the elements that are not easy to look at via AA. By and large, those are the nonmetals, and then the sort of super radioactive elements. And so the compounds, the elements that most organic molecules are made out of, we can't really identify very well. Carbon, hydrogen, oxygen, nitrogen, these things we can't see very well in AA. And so it's not useful to do an elemental determination for purely organic stuff. On the other hand, because we can't see those very well, it's nice for us to be able to sort of disregard those. If we're looking for impurities in an organic compound, we can disregard copper and all that stuff. UV-Vis can be quantitative or qualitative. Again, remember the difference there being quantitative, we can tell how much there is. Qualitative, we can tell what it is, right? Because we lose so much molecular information, AA is not very good at being qualitative. Yeah, I can tell you what element it is, but you're probably looking for that element already if you're running AA. And so this is almost exclusively a quantitative instrument. And we're talking about limits, detection limits of 0.01 to 0.1 part per billion, right? So that's 10 to 100 part per trillion, which is pretty good. Pretty good. One of the main differences between AA and UV-Vis is that, again, when we think about this as being a molecular, UV-Vis as being a molecular technique, we're talking about molecular transitions. When we look at the Jablonski diagram, for example, right? We had our S0 and our S1, but what was built off of each of those levels? Each of those electronic levels?
The vibrational energy levels.
Absolutely, vibrational levels. And so what did we call those transitions? I don't know if I actually wrote it down or just said it. Do you remember? Combination of vibrational and electronic, we called them vibronic. Do you remember that? Maybe I said it, maybe I didn't. So in UV-Vis, we have relatively broad vibronic transitions. Again, that's vibrational and electronic. And so remember in the Jablonski, we talked about how going from S0 to S1, and then you had these vibrational levels built off of each one. And so you could have this transition, 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 right? This is just to show you that the reason UV-Vis is so broad is because there's no one single transition that we're looking at, right? We're looking at sort of this set of transitions. In atomic absorption, in theory, this should be infinitely narrow. Because there's no vibrational energy levels, and we're just going from the S0 to the S1. And the S0 has a very well-defined energy. The S1 has a very well-defined energy. And so that energy transition should be exactly a certain energy for every atom, for every element. And so in theory, again, this should be infinitely narrow. And it turns out that it is very narrow, but maybe not infinitely. We'll come across a few more differences, especially in instrumentation, but in technique and in theory, these are the main differences that we see between UV-Vis and AA. All right, so the most common variety of AA is flame atomic absorption. And so let's do a quick block diagram for our flame. We start with our light source. And this one kind of goes, the block diagram looks a little bit more like those diode array spectrometers because we go directly from the source to the sample. The sample in our case is in a flame. And so, yeah, I have colors. And so then our, after it goes through the source, or sorry, from the source through the sample, we go through the monochromator to the detector, and then to that computer, right? That's the signal processor and the readout. Okay, and so this looks very similar to the diode array variety of UV-Vis that we talked about, where the monochromator and the sample are reversed from one another. There's no cuvette, right? This is our flame. The sample is in the flame. And the heat of the flame is what we use to break down that molecule into its constituent atoms, right? That's how we get elemental information from a molecular sample. We'll come back and we'll talk more about each of these pieces in a bit, maybe today, maybe Wednesday. But before we get into the instrumentation, I want to talk a little bit more about theory. But we need to understand that the fire, the flame part of this, is what affects a lot of the signal that we get out of an AA. And so there's our block diagram for an AA. We'll come back to it a few times here. So if you've ever done an atomic absorption lab, or atomic emission lab in Gen Chem. Maybe you looked through those black spectroscopes at some elemental light source and you saw the individual lines, right? I know that if you were in my Gen Chem, you did. Here we have this little image at the bottom is the calcium emission spectrum. And so it shows us the line width of each of these lines. If you look, even though they're all very narrow, they're not all exactly the same, right? There are a few of them that seem to be a bit narrower, a few of them that seem to be a bit broader. And so even though we talk about these transitions as being infinitely narrow, some of them do have a little bit more bandwidth than others, right? Some of these transitions occupy a little bit more of that wavelength space than others do. And so the realistic line width of these transitions is anywhere from 10 femtometers to around 50 picometers. Right? So again, if we're talking about a nanometer, or here we've got sort of 500 nanometers-ish wavelength of light, a bandwidth of 50 picometers even is still pretty narrow, right? That's let's see, 5 nanometers will be 1%, and so 50 picometers is 1% of 1%, so 1/10,000th is the breadth, and if it's down near 10 femtometers, it's even narrower, right? And so these are very narrow transitions. One of the reasons that AA is so good at identifying atoms, different elements, is because most elements have at least one transition that's not overlapped by any other element, right? Even though we've got 118 different elements, because these transitions are so narrow, most elements have at least one, and if not one, a dozen transitions that don't overlap with any other element. Okay, so even though they're not infinitely narrow, they're still pretty dang narrow, especially when we compare it to UV vis. There are several sources of line broadening. The first one we'll talk about is Doppler broadening. Who can give a quick summary of the Doppler effect?
And like as the sound source is moving towards you, the frequency increases.
That's right. So it works for sound, but it also works for light, right? And so as any frequency emitting thing, moves towards you, it's going to appear higher in frequency. If it moves away from you, it's going to appear lower in frequency. And so are any of you big into astronomy? You love stars? That's okay, we're chemists, not physicists. There's something in astronomy called redshift and blue shift. Sounds a bit like a Dr. Seuss story. But the planets or stars that are moving toward the telescope that's imaging them, right, seem to be moving a bit faster in reality than they are. And so those are blue shifted because that's a higher frequency. Objects moving away from a telescope seem to be moving a bit slower than they are because, and so they are red shifted to a longer frequency. And so this Doppler broadening, again, if I've got my flame, here in my flame, I've got a green sample atom, and I've got my light coming in. So this is my light from my source. If the light source and the atom are moving toward one another versus moving away from one another, or in the same direction, I should say. If they're moving toward one another, then that molecule, right, will absorb at a slightly higher frequency than if it's moving away from it. It'll absorb at a slightly lower frequency, right? So this guy here seems to have a slightly higher absorption frequency. And this one will be slightly lower. Keep in mind that while these atoms are moving quickly in a flame, they're not moving anywhere near the speed of light, right? And so even though the slower one is still moving the same direction as the light is moving a whole heck of a lot faster. It's just, so it's going to seem that it's just a tiny fraction slower and therefore a little bit lower in frequency. Okay. And so this is Doppler broadening. It can cause some of that line width that we were talking about. Another type of broadening is lifetime broadening. Those of you that took PChem 2 should know a little bit about this. Did you talk about this in PChem 2? Lifetime broadening in spectroscopy? Well, maybe not, but I know that you talked about this. PChem 2, yes? What is it, Caroline?
We did a whole lab on it. We had to do it on the board. I got nothing. I don't know.
Well, maybe if I gave you the right abbreviation. Who else took PChem 2? Russ? Savannah? Famous German physicist? Heisenberg.
Oh.
The Heisenberg uncertainty principle.
Mm-hmm.
Is this familiar?
Yes.
Okay. The Heisenberg uncertainty principle tells us that we cannot know a particle's position and momentum at the same time. Another way of saying that is we can't know its energy and its speed at exactly the same time. And so if we look at this, for lifetime broadening, the Heisenberg uncertainty principle, let me write that out here. Heisenberg, E before I. The Heisenberg uncertainty principle tells us that as the lifetime decreases, do you remember what I mean by lifetime? Think back to Jablonski. We talked a little bit about lifetimes. Which had a longer lifetime, fluorescence or phosphorescence?
Phosphorescence.
Phosphorescence has a longer lifetime than fluorescence, right? And so that emission happens much slower for phosphorescence than for fluorescence. Here, when we talk about lifetime, we're talking about how if we excite an atom with our light source, how quickly does that atom then get rid of that energy and fluoresce a photon back out? Right? And it's should be relatively straightforward for us to recognize why a short lifetime is a bad thing. Right? If we absorb a photon and then immediately release a photon, if it's nearly instantaneous, then it's almost like that absorption never even happened, right? Because the detector doesn't see the fact that we're missing a photon, right? We absorb one and then we re-emit it immediately. Now the thing about that emission is that it happens, we call it anisotropically. Isotropically. It happens all around the sphere that is the atom. It could happen in any direction. And so even though I absorb it in one dimension, it doesn't necessarily have to emit in that same direction. It could emit anywhere isotropically around that atom. Anyway, as the lifetime decreases, so the lifetime of the excited state decreases, in order to maintain this inequality, the energy gap, that energy difference between our, I'll just say S0 and S1 because that's really what's happening, can vary. Right? This is where quantum mechanics is kind of weird. The faster that transition occurs, the more the uncertainty in that energy difference, right? And so for transitions that occur very quickly, that uncertainty is very large. And so it could be that it's, just for example, 2.1 times 10 to the negative 19 joules or 2.0 times 10 to the negative 19 joules, right? Doesn't seem like a whole lot of difference, maybe a rounding error if we were doing it by hand. But that is the difference in energy due to the uncertainty principle. It's probably, in reality, not even that large. And so let's see, there's a question in our textbook that has us calculate this uncertainty. And so if we have, so we're going to calculate the bandwidth. I'm going to copy and paste this into a new slide. Give me just a hot second. All right, here we go. So we're going to use the Heisenberg uncertainty principle to calculate the minimum theoretical bandwidth associated with an electronic transition centered at 500 nanometers, given a lifetime of 10 nanoseconds. First is that we need to calculate the uncertainty and the energy given that lifetime. And so delta E, that's the Heisenberg uncertainty principle. Delta E delta T is greater than or equal to H bar on 2. Everybody know what H bar is? Sorry, I should have said that if you haven't had PChem 2. So H, remember, is 6.626 times 10 to the negative 34 joules seconds. There's a constant for your card. H bar is just H divided by 2 pi. If you were in PChem 2, maybe you memorized what that was numerically, but I didn't. 1.05 times 10 to the negative 34. I don't remember. I knew it once when I was in PChem. So we know that our time is 10 nanoseconds. And so we're going to convert we're going to figure out what our bandwidth is in terms of joules first. So delta E equals 6.6, I'm doing Avogadro's number, 6.626 times 10 to the negative 34 joules seconds divided by 4 pi, right? Divided by 2 pi to get h bar, and then divided by this 2 gives me 4 pi, times 10 nanoseconds, that's 1.0, times 10 to the negative 8 seconds. And calculator. So this is a very small energy difference. I got 5.27 times 10 to the negative 27 joules. Okay. So we're talking about a very small energy difference. So with visible light, like this 500 nanometers is, usually energies are on the order of 10 to the negative 19 joules. Right? So if our window is 10 to the negative 27 joules, right? This is in the eighth decimal place of our number, and so this energy difference is not huge. Okay. So we're going to take this energy difference and apply it to the wave equation, so that we get our bandwidth out. And remember that E equals H nu equals HC over lambda. Okay. And so if you take because we're talking about a delta here, if you take the derivative of this, relative to because we want to get delta lambda, right, out of this. And so we do some math. And we get that delta lambda is equal to delta energy times lambda squared on HC. And so our bandwidth in terms of wavelength is that energy, 5.27 times 10 to the negative 27 joules, times lambda squared. That's what we're, that's where we are. So that's 5 times 10 to the negative 7 meters squared, divided by H, 6.626 times 10 to the negative 34 joule seconds, times C, 2.998 times 10 to the 8 meters per second. Okay. Yeah, it is A-okay with me if you just write this already derived equation on your equation sheet, equation note card. 5.27 times 10 to the negative 27 times 5 times 10 to the negative 7 squared divided by 6.626 times 10 to the negative 34 divided by 2.998E8 gives us 6.6 times 10 to the negative 15 meters. And so that's 6.6 femtometers. That's not a whole lot of band broadening. If we're talking about a nanometer, right? That's not a whole lot of broadening. So a few millionths of a nanometer as our bandwidth. Now, of course, this is lifetime broadening on top of Doppler broadening, on top of pressure broadening, on top of all the other things that are going on. And so this is just one part of the one part of what's happening. So that's how we would calculate that lifetime broadening for any given transition. As long as we know what the wavelength is that the bandwidth is centered around, and as long as we know the lifetime, we could calculate this. The other thing we could do is that we could assume that lifetime broadening was the only kind of broadening, and if we know the bandwidth of a certain transition, we could work backwards to calculate what the lifetime of that transition was. Right? And so just work this entire equation backwards. Either of those is possible. Okay. Again, this example's straight out of the textbook if you want to dive in and take a look. All right, so what else is there in terms of broadening? There are two other types. The first is pressure broadening. Were there any questions on that? Sorry. Do I need to go back? Yeah. I understand why you're muted, and I'm fine with it. But if we're in a real class, even if you're not saying anything, there's always some odd looks to one another, or what did he just say? What was he talking about? That kind of thing. With online, there's not so much of that. So I feel like I don't have a feel for how you're doing as much. Anyway, there's also pressure broadening. And so in pressure broadening, this is caused by collisions. And so if we have some collisions of our atoms, these can affect that ground state energy, right? The more collisions we have, the more that atom is sort of jostled around, that ground state energy can be affected. So the S naught, right? And so if that S naught energy is changing just a tiny bit, then of course that transition from S naught to S1 and vice versa is also changing. This is because we're dealing with high temperatures in a flame, right? High temperatures means increased kinetic energy, means faster moving molecules, means more collisions per second. And so this is a big cause of broadening in AA. So this is a major cause of broadening. And can be on the order of 1 to 10 picometers. So remember we talked about the normal breadth of a transition being anywhere from a few femtometers to 50 picometers. Pressure broadening can contribute a big chunk of that, up to 10 or probably even up to 15 or 20 picometers, depending on the pressure you're operating at. Now, outside of AA, pressure broadening is a good thing sometimes. In the xenon flash lamp that we talked about as a source for UV-Vis, right? Xenon's just like every other element. It has these very discrete transitions, these very discrete emissions, kind of like we saw for calcium earlier today. But if you put it in a high enough pressure, then those individual lines broaden enough that they form this continuum spectrum. And so that's why we can have xenon as a source in UV vis. That's why we have xenon headlamps as well. If you have a car with a xenon headlamp, it works because the pressure inside the bulb is high enough that we sort of force those atomic transitions to broaden into a continuum. The other type of broadening is magnetic. This is sometimes called spin orbit effect. I don't know how much Dr. Arrington covered this in PChem 2, but it's a very PChem 2-y thing. Right? Because we usually look at atoms with more than one electron, hydrogen is not very well detected in AA. And so we're usually looking at atoms with multiple electrons. And so each of those electronic orbitals have some angular momentum, right? And so the orbital itself has some momentum. The electrons within it have some momentum. And so if the electron spin is in the same direction as the orbital spin, you get one set of magnetic field. If the electron spin is opposite the orbital spin, then you get a different magnetic field. And because of this, you'll get some different absorptions. If they're coupled parallel to one another, then you'll absorb a slightly different energy than if they're anti-parallel to one another. And so, or how that electron interacts with the actual angular momentum of the orbital that it's moving into affects the how much energy is absorbed, how much energy is required to do that transition. So let's just draw out a little diagram here. Okay. So this is our ground state. Oops. S0, S1, S0, S1, one more, S0, S1. Okay. The orbitals themselves can have some angular momentum, and so, we call these spin up and spin down. Just for the sake of argument, I'm going to use the same sort of nomenclature. If this one is spin up, if our excited state is a spin up excited state, and we do this, right, then those spins are anti-parallel. We have the spin up of the orbital and the spin down of that electron. And so that's going to be a slightly different energy than if we have a spin down orbital and a spin down electron. This can also be a pretty meaningful broadening. And so this is up to 100 picometers. But only in sort of the very largest of atoms, right? If we're talking about some smaller metals, the orbitals that we're moving into just aren't large enough to have that big of an angular momentum, and therefore, it's not as big a deal. And so this magnetic broadening, again, just due to the difference in angular momentum between the excited electron and the orbital. And there are ways to get rid of this, right? If we can sort of place the whole flame assembly in a magnetic field, which is going to sort of force more of the orbitals to have the same angular momentum. Based on the direction of that magnetic field, you're going to sort of align those orbitals. And if you do that, then you'll only get one or the other. You won't get both, and so you won't have a broader line. You'll narrow down your line. So that's one way of doing it. It's called Zeeman correction if you're particularly interested. Our book does talk about it a little bit.
I have a quick question.
Yes.
How does an orbital have a angular momentum? Is it like the other electrons in that orbital?
So the yeah, so an orbital has to be occupied to have an angular momentum. And so let me think about this. This is quantum. This is a Dr. Arrington question. It actually, this might be, so this spins must be, so the actual angular momentum must be associated with the ground state. Yeah. Because it's going to be harder, if our spins are matched, it's going to be harder to pull that electron out. And so it's going to be higher in energy. If the spins are not matched, then it's going to be easier to pull it out. So it's going to be a little lower in energy. Yeah. And so it's the orbital angular momentum. I'll put here the ground state orbital. The HOMO, if you will, the highest occupied molecular orbital. Well, it's not a HOMO, it's a HAO, highest occupied atomic orbital.
Dr. Davis.
Yes, sir.
So why is one of the orbitals spinning down on the ground state, another one spinning up when like the electrons in the S0 and S1 have like the same layout? What's the difference?
Yeah, so those electrons are spinning on their own axis, and that's what gives them a spin up or a spin down. But those electrons are also orbiting the nucleus. If those electrons are both orbiting the nucleus, traveling in the same path, then that whole orbital will have some angular momentum that direction. If they're orbiting the nucleus in the opposite path, then they'll have angular momentum in the other direction. And so just as the Earth spins on its own axis, right, it also orbits the sun. If we orbited the sun the other direction, I mean, that's the difference, right? I don't know astronomy well enough to even know if we orbit clockwise or counterclockwise. But you know, we have our own spin, and that gives us that's part of why Earth has a magnetic field. And then the Earth orbits the sun in some direction, so we have angular momentum. Our orbit has some angular momentum that way. If the Earth were to orbit the sun in the other direction, then there'd be some angular momentum in the opposite direction. And that there's a very small magnetic field due to the orbit of the Earth one way or the other way. And if the electron that's orbiting the nucleus, those two electrons have if that orbital has the same spin as our electron, then it's going to be easier to pull that electron out because they're not matched. Remember, when we say matched spin, we mean one up, one down. It's going to be easier to pull it out if they're both in the same direction than it is if it's in opposite directions. Okay. All right. Maybe I'll see you tomorrow in lab. I don't know. If not, I will let you know. Ta-ta.
Bye. Thank you.